This part of the test will measure your listening ability when it comes to conversation and lecture in the academic setting. We will listen to a recording and then answer questions about it. During the test, you can take notes what you want. I recommend you take the notes main ideas and some examples because mostly the questions come from the main idea, attitude, and of course detail. Try to understand generally, not in specific details. For example, sometimes numbers are important, but sometimes not. Try to understand the whole of the speaking and the lecture. Now it is time to listen to the lecture. Listen carefully.
General relativity, which explains how mass affects space-time curvature, has, as a result, led to the discovery of black holes. When a big star runs out of fuel and collides with itself due to gravity, a black hole is created. The star's core is crushed into a singularity, a region of infinite density. The event horizon, which stands for the boundary between which there is no turning back, is an area that surrounds the singularity. Light cannot escape the black hole's gravitational pull since it is contained within the event horizon. Black holes may be a rather confusing notion, as you can surely understand, but their research has produced significant advances in our comprehension of physics and gives us important insight into some of the most severe circumstances in our cosmos. In fact, it is particularly intriguing to consider that something so enigmatic may have such a significant influence on how we see reality. Black holes can range in size. While supermassive black holes, which are found at the center of galaxies, can have millions or even billions of solar masses, stellar mass black holes are typically about 10 times as large as our Sun. The existence of intermediate mass black holes, which fall between these two classifications, has also been proven by recent research. The idea of Hawking radiation is strongly related to the physics of black holes. This phenomena, which bears Stephen Hawking's name, describes the ejection of particles from a black hole as a result of quantum effects. Contrary to popular belief, this implies that black holes radiate a very slight glow and are not completely black. Black holes may even lose mass over extraordinarily long durations and eventually evaporate as a result of Hawking radiation. Scientists are frequently intrigued by the so-called information paradox, which is one feature of black holes. The fundamentals of quantum physics state that information cannot be lost. However, when something enters a black hole, it appears as though the data is lost forever. The concept that information might be contained in the black hole's event horizon, or that it could be indirectly retained in some other way, is only one of the many possibilities that have been inspired by this seeming contradiction and have generated significant discussion. To sum up, the study of black holes offers us a singular chance to investigate the underlying physics and the makeup of the cosmos. Black holes continue to be a rich source of inspiration for academics and an inexhaustible source of intrigue for all of us, despite their elusive and cryptic nature.
What is the main idea of the lecture? How does the professor feel about the impact of black holes on our perception of reality? What is the professor implying when they mention that information could be indirectly retained, in some other way in the context of the information paradox? What does the professor mean when they say that black holes are particularly intriguing? When the professor discusses the information paradox, what is the deeper meaning they are trying to convey about black holes? What does the professor intend to convey with this statement?
Black holes continue to be a rich source of inspiration for academics.